I would like to talk about a work that I've done some time ago with David Kaplan, Misha Stefanov, John Wang Lee, and it's called Conformality Lost. And there is another paper that I wrote with Andreas Karp, Ethan Thompson, Christian Jensen on the realization of the mechanism of losing conformality, as I will tell you. Okay, so the motivation of the talk is the following. Let's consider QCD at large a number of color and large number of flavors. In this regime, the parameter f divided by nc can be changed continuously, because nc is large, so the fact that nf has to be integer doesn't make this nf over nc to jump too much in each step. We know how the properties of QCD, and for now let's consider just non-supersymmetric usual QCD with nf massless flavors in the fundamental representation. We know that nf over nc can be changed continuously, and if nf over nc is close to the value 11 over 2, which is special because this is where asymptotic freedom is lost. If we stay on the side of 11 over 2, which is we have minus epsilon, we know that the infrared behavior of QCD is governed by an infrared fixed point called the Bang-Sachs fixed point. At that fixed point, the theory is a conformal field theory, which is weakly coupled. And the reason we know that is because we can write down the perturbative two-loop beta function for QCD in this regime, and we have the beta function to start with minus epsilon times g cubed. The epsilon here is the epsilon that stays here, so it is small, plus something that is of order 1 times g to the 5th with a positive sign. And so the beta function has a 0 at small value of g, and we can trust the renormalization group flow from 0 to that fixed point. On the other hand, if nf over nc is small, we anticipate that the behavior of the theory in the infrared should be the same as QCD, roughly speaking, and the theory should have confinement, chiral symmetry breaking. So there must exist, the two regimes are different from each other. There must exist transitions, at least one transition from one regime to the other. So let's assume the simplest possibility that there is one phase transition in power of nf over nc, and then we would have a conformal window when nf over nc is between 11 over 2 down to some value, and then the theory is non-conformal. There is a chiral symmetry breaking, and the value of the chiral condensate break conformality. So you have a transition between in the simplest scenario, there is one phase transition between conformal theory and the non-conformal theory.
Now, in the supersymmetric context, there were many different things that happened.
In the supersymmetric context, there is things that happen. Yeah, there are conform, but in QCD, we don't anticipate this thing to happen. At least I don't see a reason why why it doesn't happen.
There was a phase in supersymmetric where
Coulomb
does not break, I guess, for some.
And
there is
the
a
big
Coulomb
phase between NF and 3 by 2 NF in which you got the dual magnetic phase. Right?
Yeah. No, this is a logarithmic. Yes, running. Okay, so so what kind of possibilities can we anticipate for this phase transition? It could be that we can look at the behavior of psi bar psi as the value nf over nc is dialed to the critical values. Okay, so psi bar psi is a dimension full quantity, so we have to normalize it to some scale, but there is a scale. here, that is lambda QCD, because there is using the two-loop beta function, we can always define lambda QCD and measure psi bar psi in terms of that lambda QCD. So since psi bar psi goes to 0 at the critical point, one possibility is that it goes to 0 as a power law with some power beta. That would be a critical exponent of a second order phase transition. So this behavior is very similar to a behavior of a typical second order phase transition. But if one think about that a little bit more, there is a difference between our case and the case of a second order phase transition. In a typical second order phase transition, conformal symmetry is realized only at one point. That is the critical point. If you step away from that, the theory is no longer conformal as a scale. Here the system that we have is conformal for all value of x that is bigger than this x critical. Okay? So it is seems to be a different type of phase transition between a conformal theory and a non-conformal theory.
Sorry, what about confinement? Is it confining in this?
Okay, so it is confining here at 0, at small nf over nc. At say nf equals 0, the theory is confining.
Right, and
okay.
after x critical is?
Well, when x is of order 1, there is no criterion for confinement anymore. But there is a chiral symmetry or the parameter that can be used.
The actually is asking, is there a mass gap?
There is no mass gap. There is a pion. Yeah, there is a pion here. Yeah.
The glue ball will
The glue ball will be. I would since there is a pion. I don't know how to say this sharply. Gluon can decay into 2 pions, and the decay is not suppressed if NF is of order NC. So the gluon is the same as the sigma meson, which then, yeah. Another possibility is the Berezinski-Kosterlitz-Taules phase transition. That is a different type of phase transition that we know about. In this phase transition, there is scaling. The phase transition happens at some critical temperature. Above that critical temperature, the mass scale, or in condensed matter physics, the inverse correlation length is finite, but the inverse correlation length goes to 0 exponentially as one approaches the critical point. And then this mass parameter remains 0 at t less than tc. Okay, so the theory is conformal all the time here, and there is no conformality at t bigger than t critical. If that is the case of QCD at large NF and NC, then the chiral condensate goes to 0 exponentially with all derivative vanishing as x goes to x critical. Okay? But the physics of the BKT phase transition, as I will explain, is very specific for 2 dimension, while QCD is a 4-dimensional theory. So a priori, we cannot conclude that the BKT phase transition should be the universality class of the phase transition in QCD. Nevertheless, if we look at the existing literature where people try to find the behavior of QCD near the phase transition, you notice a very interesting thing. So you can make uncontrolled approximation using the Schwinger-Dyson equation. Write down the equation that controls the value of the chiral condensate, and then write down a self-consistent equation that determines the condensate. You have to truncate the set of equations because here you're working in the regime of strong coupling. Any truncation one does would break gauge invariance normally, so people have to do that truncation and then argue that one gauge, his or her gauge is better than the other gauges. But then if one does that, we see that the scaling of the condensate is exactly the Berezinski-Kosterlitz-Taules scaling. So the calculation is uncontrolled, but the question is, maybe this approximation gives the right scaling for the condensate. Okay, so let me now go completely to another. Yeah.
That has something very nice. Is this essentially singularity in X critical allowed by, say, Yangli's theorem? Usually for phase transitions, you just know that there's some non-analyticity partition function. But this would require some sort of essence of singularity, right? As a written for T critical. That's an essence of singularity.
Yeah, I don't know any contradiction, but yeah, it is there in the Berezhinsky-Kosterlitz-Tauris phase transition. So I think it's there must be a way around any constraint. We are taking the large volume limit, so the behavior of the partition function in the large volume limit is I don't know how to think about that. Okay, so let me now show you another example where there is a Berezhinsky-Kosterlitz-Tauris scaling that is realized in a very different context. Let us take quantum mechanics with 1 over r square potential. This is something sometimes is used to illustrate the conformal invariance. 1 over r square. There is quantum mechanics is 1 over r square. Potential has many interesting properties, which one of these is that if we try to solve these equations, the Schrödinger equation, we have to be careful with the boundary condition at r equals 0. When r is near 0, we can neglect the energy term on the right hand side because this will be much less than the potential energy term. So we are left with equations that has two homogeneous solutions, a power law solution as a function of r. The short distance behavior of the wave function can be 1 over r to the nu, where nu is this depends on the coefficient of the 1 over r square. Now, if alpha is bigger than minus 1 over 4, then we can realize conformal quantum mechanics. But if alpha is less than minus 1 over 4, then the power law here becomes imaginary, becomes complex, and we have to regularize the potential. And the way we regularize it will break conformality. The quantum mechanics becomes non-conformal. The 1 over r square potential with no cutoff would leads to falling to the center. But an interesting question to ask is that what happens if we regularize the case alpha less than minus 1 over 4 by, for example, cutting off the 1 over r square behavior. Here I just cut off and put an infinite wall in the potential and ask the question, what is the bound state energy? The system will try to fall to the center, but there is a cutoff here. What is the value of the binding, the ground state energy? And the ground state energy has the energy, has the following value, that is 1 divided by mr naught square. This is determined by dimensionality. The only scale in the problem is the length scale, is the cutoff scale. So clearly energy has to be this. But if alpha is very close to the point where the theory is conformal, then the dependence on alpha is again exponents of 1 over root of the distance to the critical point. Okay? So
should that be a plus alpha in the denominator? That is for alpha equal to 2?
Yeah, okay. plus alpha. So it is basically alpha star minus alpha minus alpha star. So we see here that in the context of quantum mechanics, the same scaling of the Berezhinsky-Kosterlitz-Tauris phase transition is again realized. Okay, in a context where there is a transition between a conformal theory and a non-conformal theory. So the question is, why is that the case? There is 3 transitions seem to have the same scaling. The Berezhinsky-Kosterlitz-Tauris phase transition in quantum mechanics is 1 over r square potential, and the chiral phase transition, if one believes the Springer-Dyson approach to give the right answer. Is that a pure coincidence, or there is a deeper reason for that? Okay, so in the language of renormalization group, how one can think about the loss of conformality. Conformality in the infrared means that there is a fixed infrared fixed point. If we lose conformality, that means this fixed point goes somewhere. We cannot approach this fixed point anymore. It could be that the fixed point goes to 0, and then we can approach that fixed point only logarithmically. So we don't have the infrared conformal theory. It might be that the fixed point moves to infinity, and we would go, the coupling constant would go to infinity. Say, if one naively try to interpret what happened in supersymmetric QCD in the magnetic phase, that is similar to that. The magnetic coupling goes to 0, the electric coupling goes to infinity. I don't know how to say. It's probably not rigorous.
Sort of suggests that this might be a free theory, right? Because there's one description in which the coupling is.
Yeah. But there is one possibility that I want to illustrate here. That is, the fixed point actually, two fixed point merges and then disappear into the complex plane. Imagine that we have a beta function of a theory that looks like this, and then we would have two fixed points. One fixed point would be a infrared stable fixed point. The other fixed point would have one relevant direction. Now, as we tune this parameter alpha in the beta function, the two fixed points merge at one critical value of alpha and then disappear. And that means that below this alpha star, we would no longer have any fixed point. We would have no possibility of conformal behavior. So what this picture gives you is that it will predict how does the behavior of the infrared scale, how the infrared scale behaves if you tune this parameter to be just on the non-conformal side. So imagine we have a beta function that goes almost to 0, almost touches 0, and then go down. And we follow the behavior of the coupling constant as we zoom into the infrared. There is a running, the coupling constant run, but then it approaches this tip, the maximum of the potential, where the beta function is very small. So it lingers, the coupling constant would linger here for a long time in the renormalization group's time, and then resume running after some time. And then it goes to infinity, and the theory develops, say, a mass gap or something. Okay, so if one now estimate what is the time it takes for the coupling constant to overcome this barrier, we see that the time is 1 over root of the distance from the horizontal, from 0 to the maximum of the beta function. So exactly this behavior is the behavior that we have seen in the Berezinski-Kosterlitz-Thouless phase transition. So this might be the explanation, if it is true. If this is correct, then another consequences of, so this picture is nice because it gives the BKT phase transition, but it makes a prediction for alpha bigger than alpha star, that there must be two fixed points instead of one.
The second one is a repulsive fixed point.
It has one relevant direction.
Yes.
Yes, one relevant direction. There is two fixed points, one infrared stable, the other has one relevant direction. And one now recall one feature of the ADS-CFT correspondence that has been mentioned here in the talk, that if one look at the correspondence between operator and field in the ADS-CFT correspondence, there is a formula: delta times delta minus d equal m square r square. Delta is the dimension of the operator, and m is the mass of the scalar field. There is a Brighton-Lohner-Friedman bound. M square has to be bigger than minus d square over 4 for the scalar to be stable in ADS. But in the regime where m square is between the minimal value and the minimal value plus 1 in the unit of and I choose the radius of the EDS space to be 1. There are two different boundary theories that correspond to the same boundary theory, the same bulk theory. And in these two conformal field theories, the scalar has different dimension, delta plus in one case and delta minus in another case. There's two different ways to quantize the bulk theory that correspond to two delta plus and delta minus. The difference between delta plus and delta minus is less than 2. Sorry, it has to be 2 here. And the loss of conformality in this case can be thought of as m squared dropping below the BF bound. Okay, so you have, if m squared, if you look at the m, imagine that one can tune this m squared by changing some parameter of the theory. There is a range of parameter where we have two fixed point, two conformal field theory, two fixed point, one that has the right number of relevant direction. One is completely stable, the other has one relevant direction. They merge, and at the BF bound, at m squared equal BF bound, they merge, and then if m squared is dropping below BF bound, of course there should be no conformal theory at all.
If you go to the other end of the window, that's just one of the CFTs running off to infinity.
There is no CFT anymore, right? If
you go to the other end, the upper end of the window, not the end.
Upper end. The upper end of the window, we know there is the Banzak's fixed point, but we don't know if there is another fixed point. And that I will talk.
I meant within ADS CFT.
Oh, within ADS CFT.
Window of n squares.
It is within when you reach this point, the dimension of the operator becomes that of a free field. Yeah. So near that upper window, one operator becomes that of free field. So I don't know if it goes beyond that, what would happen. But there cannot be a conformal field theory with a dimension that is less than that of free field. Okay, so but this picture has to be tested. That there exist theories where the loss of conformality is due to the merging of two fixed points. And let's go back to the simple example of quantum mechanics with 1 over r squared potential again. Can we interpret the loss of conformality and in this quantum mechanical example in the RG language? And to do RG, let us regularize the potential so that it is 1 over r squared, but then we replace that by a step function. It can be any function here, but the step function is nice because we can solve the equation explicitly. The value of the potential here is parameterized by a dimensionless constant g. So I put mass to be 1, so g is dimensionless. And we ask the following question. So, if I change the value of R naught, can I keep the low energy physics, namely all the scattering at very low energy, unchanged by adjusting G? Okay, so I have this potential. I make a modification to the core that is very small. All the physics I'm interested in are very low energy physics, say scattering of a particle at very low energy. There must be one family. There must be a way to change the value of G here at the same time as changing the value of R naught. That makes the low energy physics unchanged, and that would determine the beta function for G. G is the coupling constant. And the beta function for G can be computed explicitly in quantum, just doing quantum mechanics in matching. And we get this function, and let me plot the function near. So it's alpha equals 0. There are two fixed points. One fixed point corresponds, alpha equals 0 means that there is no potential. And one fixed point is just a free theory, free particle. The other is some fine-tuned square well. But at alpha equal minus 4, the two fixed point merges. So we see here that in the quantum mechanical example, the loss of conformality has a nice interpretation in the RG formalism. the coupling constant here is the one can think about that is the point-like square well interaction between the particles. Okay, so what are the two fixed points? If one look at the Schrodinger equation here, the Schrodinger equation has again, let's recall, has two solutions, two independent solutions at small r, and by doing matching condition, matching calculation, what we obtain is the relative ratio between these two coefficients outside the hardcore square well. Has two solutions, and C plus over C minus depend on the short range part of the potential. And choosing one of them to be 0 would lead to a conformal, means that the quantum mechanics is conformal. We require the wave function to be power law at 0. So a generic short range potential flows to C plus equals 0 because one of these solutions is less singular than the other, and we naturally would flow to the less singular solution. The ratio between C plus and C minus typically depends on the range of the potential. And we need to have one fine-tuning to achieve C minus equals 0. So we see here there is one infrared fixed point where generically one flows to it, and there is one fixed point where we need a fine-tuning of this short-range potential in order to achieve the other behavior of the wave function. One can actually extend this analogy even further. There is a non-relativistic conformal symmetry of the 1 over r square potential. If one look at the Hamiltonian H, the dilatation operator, and the special conformal transformation that is given here, one can show that they form SO 2,1 algebra. That's written here. So, from that one can give a very nice interpretation for the for the dimension of operators that I will mention later. But right now, if you have a system that have creation and annihilation operators of particles, then the operator C is nothing but just the moment of inertia of the system, and H plus omega square C is the Hamiltonian of a system in harmonic potential. Okay, so if we have a theory with non-relativistic conformal symmetry, then we can talk about dimension of operator. If the ADS-CFT intuition is correct, then there must be an operator that has different dimension at the two different fixed points. If we have a theory with particle interacting through 1 over r square potential, we know that it can be conformal in two different ways. In these two ways, there is some operators that have different dimensions. So here, let me. I have to say that here I'm going to the second quantized formulation of quantum mechanics. So I consider a system of particles with interacting through 1 over r square potential in second quantized form, which is basically a non-relativistic field theory. Okay, so in non-relativistic field theory, there is a theorem one can prove that there is a correspondence between dimensions of primary operators and eigenstate of a few body system in a harmonic potential with frequency omega. In our case, of particle interacting with 1 over r square potential, the dimension of the operator that we are interested in is the operator psi. That is the operator that annihilates two particles, or psi-Decker would create two particles. And the dimension of that operator is the ground state energy of a system of two particles in harmonic potential. Each of them move in a harmonic potential, but there is a 1 over r square potential between them. Okay? This problem can be solved exactly. The Hamiltonian can be diagonalized exactly in the ground state is written here. you see here it is a Gaussian, just the Gaussian shape due to the potential, and then they're divided by the distance between two particles to a relevant power, so that the asymptotics of the wave function when the two particles goes close to each other is correct. And the dimension of this operator can be read out from the energy of the ground state, and they are given in this form. And you see here that in the two fixed point is organized in such a way that this operator has dimensions difference at the two fixed point, but the sums of the dimension is equal to d plus 2. And d is the number of space. And 2, one can think about 2 as the dimension, as the number associated with the time in non-relativistic physics. Omega is equal to p squared, so time has to be counted as 2. So you see here a formula that is very reminiscent of the formula in ADS-CFT correspondence, but now realized in a very simple quantum mechanical system. Okay, so back to QCD. Can we imagine a scenario where QCD would have the type of phase transition as the number of flavor is dialed below the 3 critical value? So imagine that we have some 4 Fermi coupling C, some type of 4 Fermi coupling that runs in QCD. Well, usually 4 Fermi coupling is irrelevant. It has dimension -2. The Side-Decker square has dimension 6. So the beta function start with some positive number times C, and C would go to 0. But imagine that we have some additional term in the beta function that organize it into, say, C squared that comes from iterating the 4 Fermi interaction. And then there is another term proportional to the exchange of the gluons, because if we imagine that we do Wilsonian renormalization group, then the gluon exchange between the fermion would induce, when we integrate out the degrees of freedom, would induce the 4 Fermi interaction. So there could be some term here that I would put constant. Imagine that the coupling constant runs very quickly to what would be the Banzak's fixed point, and then stay there. And then we look at the behavior of the 4 Fermi coupling. If it has this form, then it is the required inverted parabola that we need. If with the correct ratio between the coefficient, it might have double zero, and then have no non-zero in some below critical NF.
Is there some intuition why you have minus C squared?
It is the intuition why I have minus C squared. There is NJL. If one does the NJL model, we can look at how the coupling constant runs, and that's let's do it in 2 plus 1 dimension. The NJL model has a ultraviolet fixed point where this constant and this constant balance each other. So in any dimension less than 4, the NJL model of Lachen would have this. Yeah. So that would give rise to BKT scaling if that intuition is correct.
Sorry, just to hit that point where the 2 poles come together,
Yeah.
you would have to adjust the last term, presumably, right?
Well, the last term is the gluon exchange. So we assume that the theory wants to be conformal. So there is a running of the gauge coupling due to the running. It runs to a Banzak's fixed point. Okay, very quickly, stay there. And then we look at how the 4 Fermi coupling behaves.
And will you imagine that the gauge coupling is more or less the same at the 2 different fixed points?
The gauge coupling would be almost the same. It would be the same. If the 2 fixed points are close to each other, that would be the same. Right? So we have 2 theories that try to merge. And one, if they are not too far away from each other, the gauge coupling should be.
But near the Banzak's fixed point, where things are far away, presumably, then the gauge couplings could also be very different. two fixed points?
Near the Banzak's fixed point, you mean when the alpha s at the fixed point is small?
Yes.
I will mention that. I will mention that. But let me first tell you that the BKT phase transition can also be interpreted as the merging of fixed point. That it's not the form of the. We just need to look at the textbook and find out the renormalization group interpretation of the BKT fixed point, but the form of the beta function also has the form of the parabola. I will just say that. Okay, so if the QCD, if this picture is correct in QCD, then near the lower end of the conformal window there is a UV fixed point in addition to the usual IR fixed point. And in the UV fixed point, the dimension of the operator psi bar psi, for example, would be different from the dimension of operator psi bar psi in the infrared fixed point. It would be nice, though it's not guaranteed that it can be done, that if that fixed point can be found in the weak coupling regime, where you can do perturbative calculation. Okay, so we begin by asking the following question. Can we find a perturbative fixed point where the fermion bilinear, one of the fermion bilinear has a dimension that is different from the dimension in the Banzak's fixed point? Okay, why I say here 1? That is because there is actually nf square different fermion bilinears. Chiral symmetry would make them all have the same dimension. But here I assume, I will ask the following question. Is there a fixed point which break chiral symmetry, but one of the fermion bilinear, say psi bar psi, would have a different dimension than that one? Okay.
So I thought you're now working in the regime where the two fixed points are widely separated.
Well, two fixed points are widely separated. The other one may not exist at all. Right.
But now, if a given operator has two very different dimensions, then there should be some coupling constant effect going on. So
coupling constant effect. Coupling alpha s. You have in, what do you have in mind?
I meant alpha s because I imagined if alpha s was 0, then nothing. Then it's all free. Or you say it's like an NJ.
Okay, so let me first consider the simplest case, and then we make it more and more complicated, and your question might probably will be answered. Okay, so we want a theory that looks like this. So there is a Banzak's fixed point, usually here. The dimension of psi bar psi is 3 at this end of the Banzak's fixed point. We want to find another theory, that is QCD star. Right? Another theory where there is an operator, scalar operator, which dimension is different. And using ADS-CFT intuition, the sum of the dimension has to be 4, so it would start from 1 and then go up, and the two fixed points merges here. But if this picture is correct, then near this fixed point, the theory should have a free scalar, almost free scalar. And that suggests the way to write down this theory. We have start with Banzak's fixed point, then in the UV fixed point delta is 1 plus some number times the tube coupling, almost a free scalar. So we constructed the following theory. We take QCD and then couple a free scalar, a scalar field to the operator psi bar psi. Right? And then add all possible terms needed to make the theory renormalizable. And we can think about that theory as we take QCD, but we add to that theory some 4 Fermi interaction mediated by a scalar. Okay. Now we can look at the beta function, running of beta function. Beta function of the Yukawa coupling Y has a fixed point at a non-trivial value of the Yukawa coupling. So let's recall that at the Banzak's fixed point, this G square is completely fixed. We have to solve this equation and get the Y constant. And then we look at the running of lambda. Running of lambda depends on this Y. And we can find another, that this fixed point can correspond to a physical value of lambda. So the fixed point for the coupling Y and lambda exists. Running of alpha for this theory is unaffected because of NC counting. Here we add into the theory only one scalar field. The diagram that modified the running of alpha doesn't change. So we have such a theory. Okay.
Phi cube terms are prevented by chiral symmetry.
Phi cube term is prevented by this discrete symmetry of the chiral. Discrete, side by side go to minus, side by side. I think we can arrange that. Okay. So let us think about this as lacking the terminology. Let's call that model A. It's one model, and this model would have the same gauge coupling as the usual QCD, but there is one deformation of the model A that make it flowing into the Banzhaf fixed point, and that is the mass of the scalar. The mass of the scalar square is phi square is the relevant deformation, and if you make this mass square to be positive at a low energy scale, the scalar field decouple, and we fall back to QCD. So the behavior here is exactly as we expect with the picture of the two fixed point. Okay, so the previous model doesn't have chiral symmetry, so we can ask what happens if we try to make the theory to be that looks nice, that has a full chiral symmetry. So to restore chiral symmetry, we can introduce an F square scalar. So instead of coupling a scalar to just side by side, we make the coupling in such a way that the full chiral symmetry is preserved. And there is 2NF square scalar, real scalar, we have to couple to all the fermion bilinears. Now the running of alpha is affected by this by the presence of so many scalars in the theory. There is NF square scalar. NF is of order NC, so there is a change in the behavior of in the running of alpha, and we have tried to look at the fixed point for this theory, but we found that there is no perturbative, at least in the perturbative regime, there is no fixed point except for the trivial Banzhaf fixed point. So perhaps this model, so it seems that we couldn't find the correct fixed point. Okay, so perhaps the UV fixed point exists only sufficiently close to the critical ratio of NF over NC, and that question then would have to be formulated on the lattice because analytically we could not find that fixed point.
Why does it have to have chiral symmetry?
Why this has to have chiral symmetry? Because near the critical, I imagine the following, that we have at the lower end of the conformal window there are two theories. One theory is the usual Banzhaf fixed point. The other theory is something that can be thought of as this Banzhaf fixed point plus 4 Fermi interaction. Now, if my intuition is right, then when the two fixed points are very close to each other, what happens in order to go from one fixed point to the other, I add a small 4 Fermi interaction, which can be done in a chirally symmetric way. I'm also not very sure if I need the other fixed point need to be chirally symmetric or not. So I'm rather confused about that.
In your original QCD-like motivations, at least it should have been chirally symmetric. That is, you were trying to explain the Schwinger-Dyson.
Yeah, I'm trying to explain the Schwinger-Dyson behavior.
For that purpose, you do want to preserve chiral symmetry in the Lagrangian.
In the Lagrangian, and then I would like to do that, but I'm not sure if this is necessary for the argument that I'm presenting, that the behavior of the condensate the behavior of the condensate is BKT. Basically, what I'm saying is that I am in a fixed point. Okay, if I near this window, I just need to push the system a little bit to go to the chirally broken phase. And not completely, the coupling constant is not completely, not big enough for me to form a chiral condensate. I need an additional push in the form of a 4 Fermi interaction. And that push goes to 0 as I approach the lower end of the conformal window. So I don't know if for the sake of the argument, I need the push to be chirally symmetric or not. But it would be nice to have a model that would have full chiral symmetry. And
in this one, why do you have to excite all the NF square scalars? I mean, can't you just take some SU2 subgroup of SUNF and so that the problem here seems to be that running of alpha is being affected because NF is...
And the NF square scalars, yeah.
So I'm saying that perhaps you excite only a small subgroup.
No, but I don't know how to make the... I can do that, but then I will break full chiral symmetry into a... So I want to write down something like that. Yeah, that would be chirally symmetric. Now let's go back and then try to do some... So if this is correct, then this QCD star theory with full chiral symmetry only exists from some point at some largest coupling and then merges with this point. But we would not be able to find this theory here. Let me say, I think I don't have the slide here, but if I'm trying to preserve only a subgroup of the chiral symmetry, say I preserve here 1/2 of chiral symmetry. Yeah. So I take SU 2n cross SU 2n is the original symmetry. I preserve only SUN cross SUN. Then I can find the fixed point. And the ultraviolet fixed point in this way. The fixed point will have a different value of the gauge coupling constant, but it's still small. All the calculation can be done exactly. Only when I try to preserve the full chiral symmetry that the equation doesn't give me any answer. Okay, so now in holography we can realize the one example where there is a BKT phase transition. Consider a defect QFT described by the 3 D5 brane configurations, and that would describe 2+1 dimensional fundamental theory of fundamental matter that is coupled to the adjoint matter that live in 3+1 dimension. Okay, so we can turn on both the density of matter and the magnetic field by turning on density of a U1 charge in 2+1, and then turn on a magnetic field. And what turned out to happen in this particular case is that if we look at the behavior of the embedding parameter that would break the chiral symmetry, the embedding parameter behaves as a scalar that has a certain dimension in the IR, and that dimension drops below the BF bound if the magnetic field is too large. The dimension of that operator is depends on the ratio of the magnetic field and the density, and therefore the equation for that scalar is the same as the equation for quantum mechanics in 1/r² potential in the linearized approximation. To the nonlinear approximation, there is a term that would stabilize the quantum mechanical problem. And then we can find that the behavior of the chiral condensate is the same as the BKT phase transition that is given by e to minus some constant divided by the distance from the critical point. Okay, so let me conclude. The merger of annihilation of fixed point explain the loss of conformality in various systems. For example, we found quantum mechanics in 1/r² potential. We find that in the Berezinski-Kosteritz-Taulis phase transition. And there are some other field theories which we can write down that would behave in a similar way. It is conceivable that the chiral phase transition in QCD as a function of NF over NC also has a BKT scaling. That would imply that there is a UV fixed point in QCD with a fine-tuned 4 Fermi interaction, at least close to that end of the conformal window. One can think about this loss of conformality as a violation of the Brighton-Lohner-Friedman bound in the gravity dual. The mass, if we try to write down a theory dual to QCD at that value of NF over NC, the mass square of the scalar should go to near the BF bound. The statement here, naively it would imply that the dimension of the operator that is dual to that scalar would be equal to 2 at the end of at that end of the conformal window. But I put here a question mark because I'm not sure if that statement actually is exact in QCD, even when the conformality is lost in that way. The dual theory must have NC square scalar fields, each of which has mass square that drop below the BF bound. So I don't know whether this formula of delta plus delta minus equal to D remains valid. But in people doing the Schwinger-Dyson approach, found that near the point where chiral symmetry start to appear, the dimension of psi bar psi is exactly equal to 2, and that fact was used widely in model building in Technicolor. That is the dimension that they need for extended Technicolor. Okay, thank you very much.
We have time for some questions and comments.
Two questions. First, you could have had this dome-shaped behavior of the beta function just for the gauge coupling. Or is that impossible? Why do you need to
have two? It could be also that. You have to think about, I think the correct way to think about the situation is that you have a multidimensional space of coupling constant, and then suddenly 2.220 of the beta function merges. It doesn't have to be just, you don't have to think about that in terms of one coupling constant or two different coupling constant. The invariant way to think about the situation is that two coupling constant merges. And then you can make a slice and then say that in terms of that coupling there is a...
But is it, do you find it physically, intuitively implausible that this whole behavior does not involve fermionic operators in an important way? That's all.
Well, for me, it's actually more convenient to think about the fact that it is a 4 Fermi interaction in the following way. That is, 4 Fermi interaction is the one that induced the. Suppose I am in the Banzhaf fixed point. The chiral symmetry is broken because the attraction between the fermions is too strong. In the Banzhaf fixed point, the interaction due to the gluon exchange is a little bit not strong enough for me to get get conformal, get chiral symmetry breaking. So I have to add to that some additional attraction between the fermion in order to generate chiral symmetry breaking. If I add just the right amount, then I should be sitting at the edge, at the dividing line between chiral symmetry broken phase and chiral symmetry unbroken phase, and that is the conformal theory that QCD star that I want to find.
Any other questions or comments?
Sorry, one more question. You said at the beginning of your talk that you thought that implausible that in QCD you would get this infrared free phase that you get in super QCD. The phase that you get between NC and 3 by 2 NC.
Uh-huh.
Why
is that? I don't have It could be, yeah. I cannot exclude this possibility. I know that all the argument in supersymmetric QCD that leads to this fact would not are not applicable in QCD. I know that the Schwinger-Dyson approach doesn't give that phase. Maybe it's not refined enough for that phase if it exists. If it exists, it would be very interesting situation. I think in any case, this question of what happened at the end of the Banzak's window is an interesting question. So I would like to have an answer to that question.
So if it was like super QCD, what would happen at the end of the Banzak's window is that the theory would become free, I think.
But free in a different.
Correlation functions would be of a free field.
Yeah. So presumably that is something that has to be. One has to formulate some statement that can be verified on the lattice. Say if you change NF, the dimension of some operator should be equal to dimension of free operator, for example. So I think that is also another interesting possibility.
Does that mean super QCD you don't expect this BKT scaling with your end?
You don't have actually in the if you look at the dimension of the operator, it goes linearly, and it just goes to a free. It goes straight to a. There is this behavior isn't there. I think the way I would like to think about this, maybe not correct way to think about the situation in supersymmetric QCD, is that you have a situation where the beta function near the beginning of the magnetic phase, the beta function would actually looks like that. Okay, so the Banzak's fixed point would be like that. It goes to infinity. Okay, you can check that by looking at the slope of the beta. The beta function itself is not well defined. It's depending on the scheme, but the slope of the beta function actually goes to 0 as you approach the end of the conformal window in the Banzak's in the supersymmetric QCD.
Can I just?
I don't know anyone who is attempting to do that. It probably would not give. It would have to be very refined to reproduce the real phase diagram.
But just in the spirit of the same kind of questions, if we want to test this idea that when two fixed points come together, we get BKT scaling, we might be able to rig up a supersymmetric situation. I don't have one clearly now, but we might be where you have two nearby fixed points. I wonder, and then test this idea.
Supersymmetric QCD, as I argued, would not have.
Not necessarily supersymmetric QCD, but maybe if we soup it with additional gauge loops and.
Maybe we can arrange a situation like that. I think the most interesting question is within non-supersymmetric QCD whether that would happen, and I think the situation here is rather general because we just need to draw some beta function and then compute the infrared scale, and we can argue that in 1 over quantum mechanics is 1 over R square potential, and some other field theory that I didn't present it here. You see this situation exists. Yeah.
So at this fixed point, the Nambu-Generalisimio model exists as a quantum field theory.
At the other fixed point?
No, at this.
At the UV fixed point.
Yes.
The Nambu-Lasinio model.
Where this operator
So maybe to think about that, we can think about this way. There is a QCD that has a Banzak's fixed point, and then we add to that some 4 Fermi coupling. Usually that is a bad thing to do because this is the dimension -2 coupling. But we know from many examples like Nambu-Lasinio model in large N in 2+1 that it makes sense. It actually it's a well-defined thing to do if the dimension of this operator is if the dimension of G, if the dimension of the operator psi bar psi square is less than 4+1. That is the crucial thing. So at the Bang-Sachs fixed point, the dimension of psi bar psi goes down below 3, maybe 2.5, less than 2, 4 plus 2. It might be like the dimension of that operator can be say 5.9, and in this case there is an ultraviolet fixed point of that. But this is the additional Lagrange that is added to the interacting QCD, not to the free fermion theory. If you try to add 4 Fermi interaction to a free fermion theory, there is no way one can make it to have a well-defined continuum limit. Only if one has interaction in this sector to reduce the dimension of psi bar psi square below 6. It can be 5.9, but yeah, that's.
Any other questions or comments? If not, since this is especially the last of the Chandrasekhar lectures, let us thank Professor Son for a wonderful speech.